Good afternoon. This is Scott Dowman of PowerWorld Corporation, and I'd like to welcome everybody to the next session of our user group webinars around some new and improved features in PowerWorld Simulator version 24. Today, we're joined again by James Weber, Director of Software Development at PowerWorld. And Jamie has been with PowerWorld Corporation since almost the beginning. He was one of the early employees that was hired by the founders. He has received his education from the University of Wisconsin at Platteville, and also has a PhD from the University of Illinois at Urbana-Champaign in power systems. So go ahead, Jamie.
All right, thank you, Scott. The presentation today is one I've been meaning to make for years because there are features in PowerWorld that I think a lot of our customers could get good use out of. And it's not something we usually talk about in our training just because we don't have time in a week of training to talk about this particular topic. So I was going to give that presentation today. This is part of a series of webinars we're planning on doing over the next months. Honestly, I'm sure we'll keep adding to this. The next one is scheduled for next week on Tuesday on using the EPRI GICHARM tool and integration with simulator. So I'll mention that. But the topic today is talking about a connections menu in PowerWorld simulators. So what we're talking about is in PowerWorld on the Tools tab, there's this menu over here that just says Connections, and there's a bunch of different features underneath it. I'm going to talk through most of those. All of these features, they're not, I guess I wouldn't say they're traditional power system engineering tools. They're more basic than that. They're just talking about what a mathematician would call a graph. To them, a graph is made up of vertexes and edges and weights. In PowerWorld, or in our industry, we talk instead about buses and nodes, which are the vertexes, and branches or transformers and lines that are the edges. And then the weights can be different things depending on what tool we're trying to, or how we're trying to use the tool. So just to get some words out of the way. So in these tools, the vertices are these red dots. They would represent buses in a power system. The edges are the blue lines that connect the vertices. They would represent branches. And then a weight, I mean, it could be anything. We'll show an example in a second of different options in the tools in PowerWorld. Most of the tools that we build on these topics of graphs in PowerWorld are for what's called an undirected graph. So each of these edges doesn't really have a direction assigned to it. There is one tool, it's the first one I'll talk about, which calculates circulating megawatt and megavar flows. So those edges do have directions. It's the direction of the megawatt or the megavar flow. So it's the same idea as the plain old undirected graph. The directed graph just means each edge has a direction associated with it. As far as the weights go, in the tools where we're looking at treating the edges as having a distance associated with them, all of those tools are not directed graphs. There's things like determine the path distance between buses, determine the shortest path between two buses or two groups of buses, setting things to the closest bus. Those tools will have something that looks like this part of it. On the dialog, there'll be something that looks like this. A script command will have a similar option. And the distance measures in PowerWorld, you can either use the series X reactance of the branch. We would be using the magnitude of that. You can use the series Z, so R squared plus X squared square root. You can use the length. A branch in a PowerWorld case does have a length. I'll just pull it up here. So if I'm looking at branches, there is a field called length. The important thing to know about this length is you have no idea who populated the case. So we don't really know what this is. So in most cases, you can't really rely on this to mean kilometers or miles or whatever. This is a case where it is populated, but it seems like, well, it looks like the transformers are all ones. I don't know. Maybe these lines actually, nah, probably not. Look at all these ones and zeros. Anyway, the point is the length of a branch in a power system model is a field that can be populated. Some utilities will do that, some won't. So you have to be careful with that one. Or you can just say other. I can make a custom field and populate it myself. The other options are you can do the number of nodes or buses away. You can do the number of super buses in a full topology model, and then the number of fixed num buses in a full topology model that uses those. So those will come up throughout it. But the first topic I want to talk about is the tool that looks for circulating megawatts and megabars. So I'll jump over to PowerWorld. PowerWorld does have a set of we call them synthetic cases that Professor Tom Overby has put together. Ironically, I make this joke, others do as well, that the biggest problem with the synthetic power flow case is it doesn't have any errors in it. So I can't use those to demonstrate circulating bars because, not surprisingly, it doesn't have any. So this is an example of a very old Western interconnect case. When you're in the tool, if you want to look at circulating bars, you go to Tools, under Connections, and then go to Find Circulating Megawatts and Megabars. And this will bring up a dialog. It actually already did the calculation when I opened the dialog, and we'll talk through what that means in just a second. But that's where you find it. All right, so what are we looking for in this tool? All right, the first thing is, even without this tool, in PowerWorld solution options, we do have this option in here called Disable Balancing of Parallel LTC Taps. Normally, we don't want to disable that. If you're not disabling it, PowerWorld does automatically catch very obvious situations of this. We'll look for groups of buses that are connected by very low impedance branches. And then we'll look at those two groups and say, are there transformers between these groups whose taps are out of balance with each other? And if they're out of balance, you'll get bars that circle around that we'll show in a second. So those things you don't really need this tool for because it's kind of obvious. They're directly in parallel with each other. This tool is going to be looking for more complicated situations than that. So in order to find those, we are going to represent the power system as a directed graph. So, and we're going to be looking for something that we call a flow cycle. I shouldn't say we, this is a mathematics term. We're just using their tools. So what we're looking for is a series of transmission branches that create a flow that goes in a circle. So like right here is a group of branches with directed arrows that go around in a circle. If I look more broadly, there are other circles as well. Other tool or things that will appear in the software is PowerWorld will have a threshold. So if I look back at the dialog, there's a flow threshold. It basically says that any megavar flow below an absolute value of 0.1 is treated as zero. I don't, you can get small circulating var flows just because of megawatt and megavar mismatch in the power flow, which is irrelevant. We don't want to see those. Another option that'll appear on here is there's a maximum number of related cycles. Related cycles are, when we first put this tool in, one of the problems with it is we'd run it and we'd get like 5 million circulating var flow paths. It took us a little while to figure out, what was going on is you would have little groups of, so here's 4 different circulating groups, but then there are paths between those circulating groups. And if you get more and more of these that are all connected together, you can get all kinds of combinations of circulating flows, and really they're all related to each other. So in PowerWorld, we just call these related cycles. Mathematicians use the word strongly connected graph A strongly connected graph just means that every point inside this part of the graph can be reached from every other point by following one of these arrows. So they're all kind of related to each other. So that's what that count is for. As a software tool, mostly it's just a way so that we can provide you with a list of hundreds of circulating bars instead of millions, because millions is not useful to you and takes too long to calculate. So this truncates that. So that what it's looking for, this is an example graph I just kind of made up. So you can see here, if we follow the orange arrows, we've got a circulating path that goes around like this. And then we also have a related circulating path that goes around like this in green. So that the algorithm is just looking for those things. All right, what causes circulating bars and megawatts? One thing that can happen, which isn't actually usually much of a concern, is we might have a series cap that's got, say, a small negative X value. Some power flow cases will model a very low impedance branch in series with that, or sorry, in parallel with that, with a very, 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 very low impedance. And if this is closed, then we've got a path where we have a positive R or a positive reactance and a negative reactance. You're always going to have a slight amount of circulating megawatts and megavars here, but the amount flowing on the capacitor when this is closed in is going to be very small. So those are things that you should ignore, but they do show up. The more useful things are the actual megavar flow cycles that are larger. Those are almost, I'd say, I've never seen them not caused by this. So they're caused by transformer taps that have kind of they're not well coordinated. And we'll show some examples here in a second. Megawatt flow cycles I have seen in cases before. They're much more rare. You have to have phase shifters near each other that are unbalanced, and that just doesn't happen as often in the real world. That there aren't as many of them, so there's less opportunity to have them miscoordinated. So you don't see them as often. So the examples that you'll see in a case are, here's a couple pictures where I have, let's look at this one on the right to start with. These are 3-winding transformers, but the main windings are here. Get a different ink color. All right, here and here. And then you can see that there are the blue arrows are representing vars. So you can see we've got a circulating part of vars going around and around here. And we also have some going around and around at the top. The reason it's happening is because we have these 3 tap ratios right here that are the 0.928. These two probably are coordinated. And then a third transformer got added. I suspect what happens over time is a case has, in this example, 2 parallel transformers that they set up very carefully to coordinate with each other. And then a decade later, another young engineer is handed, hey, we added a third transformer, put this in the model. They put it in the model. They get all the tap settings and everything all correct, which isn't simple to do at the beginning, but they don't make the 2 tap or the 3 tap ratios consistent with each other, which results in the circulating bars. One interesting thing, when I look at EMS cases like real-time models, I see very little of this because I'm sure in a real operations of a power system, the engineers who operate the system are very careful of this because they don't want the circulating bars. Whereas in a large planning case, it's very easy to miss this. So this tool will find those for you. So let's go back to simulator. In the tool, what you see is you just get a big table showing you instances of circulating bars. There'll be an integer here that says whether they're related. So it's saying this integer 3 says these 2 are related cycles, so they're probably the same issue. There is a column that'll show you which areas it's involved. There's a column for the loss megavar reduction. This is an estimate calculation that PowerWorld does. that says, hey, if I reduce the megavar flow in this circulating set of branches by the same amount, it's not, I mean, it doesn't really represent a power flow like calculation. It's just like, if I could magically reduce that and get rid of that circulating var flow, how much would the megavar losses in the system reduce? It's a good way to rank which circulating cycles are most important. There is a column that says what is the minimum flow in the cycle. So for instance, if these green values here represented megavar flows, the minimum flow in these cycles would be this 0.01. And then there's a X weighted, so the extra var flows on branches that have a high series X are going to create more X squared or X or I squared X megavar losses. So they're more important. So can maybe X, weight the cycle flows by that, the number of cycles. And then the most useful field is it'll show you what the min and max tap ratio is in that cycle. And usually you'll find there are at least 2 transformers that have tap ratios and they're possibly miscoordinated. A good way to visualize the results in simulator, if you're looking at the flow cycles, I can go over here to this tab and it'll show me all the branches in the system that are part of any flow cycle. So then I can add a column, say I'll add the custom integer column, and then maybe I'll set all the values so that all the branches that are part of a cycle, I just flag them with an integer 1. And then maybe I go over here to dynamic formatting, another feature people don't use a ton, but I can dynamic format a case. I can say any branch in the case that has custom integer equal to 1. I want to change the line thickness to 10 and the line color to bright pink. And I want to do this on any transmission line or transformer. I'll call this highlight cycles. Then if I go look at oh, 73022, then if I go look at the bus view, I can see them in here. So as I'm navigating around the bus view, maybe I want to change the bus view to show me megavar flows instead of megawatt flows. You can see I've got bars going here, going over here, all the way down to story. Well, actually, I can kind of see it here. It goes here, and then it comes back. So there's probably some transformer taps. There's a tap along the way. So it would be, we don't have a tool that says fix them, like the auto balancing of taps that we do for the obvious ones. But you could go through your case and fix these things. These are very common to have dozens of these situations in a power flow case. If you had a 1 line, I didn't with this particular case, I hadn't made one, but you could also then highlight them on a 1 line and kind of see the circulating paths. So you can see in this example, there's a group here of related circulating flows. And actually, this is a good example. It's like these 2 transformers here and this transformer here, they're not strictly in parallel with each other because there are transmission lines between them. But, they are going to interact with each other. So it's important their taps be balanced. All right, so that's one tool I would encourage people to make more use of. Going back to just looking at graphs again, another tool that many of our customers, I think, do use is what if I want to know how far away are all the points in the system from a particular part of my system? So in this example, I have point A. I want to know how far are all the other vertices away from point A. So then I have to define, I want to start at point A. I have to define what is my branch measurement metric. Uh, we just have some numbers on here to show it. And then what the calculation will do is it's going to calculate all the yellow highlighted numbers, which is what is the length of the shortest path from the start point to each bus. So for instance, point D says it's 0.04. It's not, it doesn't go this way because that would be 0.02 plus 0.03. Instead, the shortest path goes around in the pink highlighted value. Similarly, if I'm at bus B, it's much easier. It's just the direct path. If I'm at N, it follows this blue path to find the shortest path. So the idea is the determined path distance tool is going to do this calculation for you. Again, I'll demonstrate this. This one, I'll just use a big synthetic case. All right, so again, it's under tools. I go to connections. I say determine path distances to buses. And then on the dialog that appears, I have to choose a distance measure. In this case, I think the one I usually use is the series Z magnitude, either that or the number of nodes. I mean, the advantage of the number of buses or number of super buses is just easy to explain to someone. But, you know, we usually care about impedance too. So the Z impedance is also useful. And if I choose then a particular bus, in this case, I am sitting here in Champaign, Illinois. So I'm going to choose this fake transmission substation in Champaign, Illinois with a 500 kV bus. You can tell that Professor Oberby made this when he was in Champaign. Champaign doesn't have anything close to a 500 kV bus. So, all right, so let's go ahead and calculate it. We've got a distance measure. There is an option about which lines to process. Maybe I only want to go across lines that are closed, or I only want to go across, lines that have a custom integer value of 3. I don't know why they chose them, but we'll just do all lines in this example. And then the result gets populated in a particular field. In this case, we're going to populate it in the custom float field. So when I hit calculate, it does the calculation, and then the custom float field gets added here. If I sort by that column, the 0 value will be at the bus that I chose to start from. And then, the farthest bus away, some of them are going to be this artificial 10,000. That just means there is not a path that goes between Champaign and that bus. So there must be islands in the case. Probably there is. It's the fake ERCOT system. So there's no connection there. But the farthest away that's not 10,000 is, I'm going to guess Miami. I didn't look beforehand. No, it's somewhere in Wisconsin. That's just because of it. I assume it's because there's an enormous impedance somewhere. I didn't actually look ahead of time. But yes, that's kind of crazy. There's an impedance on a transformer in Prairie du Sac that's 105 per unit. So that's why that's so big. Anyway, that you get the idea. The advantage of a tool like this, the thing that I do see our customers use this for, a customer that's doing a generator interconnection or a large load integration study, sometimes they're like, hey, I want to monitor things that are nearby. So they'll start by saying, I'll just monitor things in my area or my zone or something. They'll just filter in that way. But they might want to say, I just want to monitor anything that's just within 10 nodes of mine, or this summation of impedances away from mine. So they can do this to to populate that custom float field. They can then use the filtering so that I can toggle the limit monitoring settings. So for instance, they would go into case information limit monitoring. They would go to lines. They might say, you know what, I'm going to filter this. Actually, let me pick a smallish impedance. So let's say they want anything that's within 0.2 per unit of that bus. So they might have a list of buses here. I could create a filter that says the custom float value has to be less than 0.2. And I could say nearby stuff to name my filter. Then if I go over to limit monitoring, I could go to the bus table and I can use that filter. And so now I'm only looking at the buses that are in that group. Actually, I want to remove it first. I want to set monitoring for everything else to no, and then apply my filter, and then toggle all of these to yes. So then I'm only monitoring those buses. I can then go to lines. Another tip people don't use a lot, but they should because it's really helpful. I want to filter the buses, but if I come here, that's the filter I made was for a bus, not a branch. But I can apply a bus filter. So if I change this to bus, I can apply the bus filter to the branch table. So what this is showing me is any transmission line or transformer that is connected to a bus that is nearby. So if either the from or the to. So again, oops, I forgot to do this again. So I could set all these to no. I could change this to nearby stuff, and then I could set all these to yes. So using a tool like that is a very quick way to do that, to choose things. Same would go if I'm doing this study again. Maybe I want to run contingency analysis and look at all the single line outages, but I don't want to do the whole case. I only want to do things within 12 nodes or something. Then using this is an easy way to do that. All right, another feature related to this is determine the shortest path between 2 points. It's a very similar calculation. It's just you're going to pick 2 points. You're going to pick a start and you're going to pick an end, and it's going to find the shortest path and then show you which branches and buses are in that path. So to do that, you just go to Tools, Connections, determine shortest path between. And in this example, I'm going to look for between Champaign again and Baltimore. Not sure why I picked Baltimore, but that's just what I picked. Now, when I hit calculate here, it calculates it, and then I get a list of buses here. The list of buses is given in the order that you would progress from downstate Illinois area, Champaign, through Indiana, through Ohio, through Western and Eastern Pennsylvania, and then through Maryland, and finally get to Baltimore. And then I can also look at the list of branches that go between there. And again, there's some tools, calculate and visualize on a spatial view one line. I can click that and it'll pop up what's called a spatial view, which has been around a while. Let me go ahead and add some borders to this. So you can kind of see it, just put them, this is a case that has latitude, longitude coordinates for everything, but you can see this is the path as it makes its way across the country. And again, my choice was by impedance. So it's jumping up to the high voltage system, going across that, and then eventually coming back down. Actually, if I were to go, yes, I start in the 500, and well, that part of the system you had to drop down, and then you kind of get eventually over here to Baltimore. So again, a very useful tool in some situations for you. It's like sometimes you have 2 buses. An example I can think of when I'm doing contingency analysis and I've got a particular line outage that seems to be overloading a particular line all the time. If you know your system really well, you don't have to do anything because you just know where it is. But if it's a system you're not familiar with, you're like, well, how close are those to each other? So you can use a tool like this to kind of figure out what is the path between them. All right, here's a new tool in PowerWorld related to this. If I go to Tools, there's something that says set the bus field from the closest bus. This will bring up a dialog. I have to choose a filter that specifies the buses that I want to set a particular value to. And then I have to choose another set of the buses that I'm looking for from those buses that I want to copy that value from. And then I'm going to, for each bus I want to set a value on, it's going to do a search to find the closest bus to it that's in this copy list. And then again, you have to specify a distance measure, which lines to process. And then when you're done, you can, the calculation, you can choose a field that says, I want to copy the value from the copy from buses to the set to buses, and I want this value to be done. So one example calculation I have seen done, ERCOT is putting out full topology cases now, but it's not completely full topology. Many of the generators in the case, I suspect they're future generators, so they don't really have a sub yet, are put in the case and they don't have a substation assigned to them. And maybe you're like, you know what, I just want everything in the case that doesn't have a sub to get assigned to the substation of the bus that it's closest to. You could use this tool to do that. You would choose the, I think I have it. Yeah, it would do something like this. The script, there's actually a script command for it, but you would choose the filter of what you want to set to be that the sub number is blank, meaning the particular bus does not have a substation assigned yet. And the one you want to copy from, you'd say the sub number is not blank, or not is blank. And you want to traverse all the branches. The distance measure is based on impedance, and the value I want to copy is the sub number. So a little script command like this, you can populate a substation for all the buses that don't presently have a sub. Now, that might not be the right thing to do, but it's quick and good enough for maybe what you're doing. Maybe the best thing to do is to go through the case and figure out where the new substations are going to be, but that might take you a week and you just don't want to spend the time. So a feature like this is useful for that. It's kind of built on top of the existing tools that had been there. All right, another tool. Get back to my slides. In PowerWorld, we have a tool we call facility analysis. So again, it's under connections and then facility analysis. And then we also just call it the minimum cut, because it's what mathematicians call the min cut algorithm. What this is going to do is we're going to choose a particular facility, which is a group of buses. We're going to choose a bunch of other buses and assign them to the external system. And then all of the other buses that are not in the external system and are also not selected are what we call the study system. What the minimum cut calculation is going to do is it's going to figure out the minimum number of branches that can be removed from the system so that they would isolate the facility from the external system. So the facility to the external system, I obviously could cut these 4 lines right here. You can always just cut the tie lines from your facility. Or I could cut the tie lines to the external system. There are 4 lines over here. But the min cut algorithm is going to figure out that inside the study system, there's actually a spot where I can cut 3 lines, and that would be the minimum cut to do them. So let's do an example. If I go to connections, facility analysis, I have to confess, I hadn't used this tool in a little while. It is kind of old and clunky, but it is useful. It's built on top of the equivalencing dialog. If any of you have ever done equivalencing, this dialog will look familiar. But I'm going to start by choosing the selected buses. So the selected buses will represent the facility. And what I'm going to do, I'm going to just add the area number to this case. And I'm going to choose area 33, which is Indiana in this case. Use a quick filter. And I'm going to set all the buses in Indiana to selected equal yes. And I'm going to remove my filter. And then I'm going to make another quick filter that says choose all of the areas that are in numbers 1 through 3. Oh, I want within integer range list 1-3. And let me just add the area column so you can see what that is. That's Maine, Vermont, and New Hampshire. And I'm going to make those the external system. So doing that, and there's various other features in here to choose things if you want, but we won't go through those. The idea is I need to go through every bus in the system somehow and assign the facility ones to have selected equal yes, and then have the external system have this which system column equal external. And again, the which system, if you look at the variable names, if you guys are using aux files, if I change this, if I change the column headings to be variable names instead, you'll see that the column header, it's equiv. It's like equivalencing, but it's just being used in this tool to select things. All right, so if I do that, I can then go over to my facility analysis. And it has gone through, it has populated a couple things here. It's tells you how many buses are in the external region, how many are in the facility. This capacity, that just represents the number of tie lines between the facility and the study system. And this represents the number of tie lines between the external system and the study system. So obviously the minimum cut is it is 90 or less, because you could always cut the ties. So I'm going to go ahead and hit find the min cut. This does take a little bit of time, not too much. This is a 80,000 bus case. It still doesn't take very long. But it says these are the 21 transmission branches that will cut those two things from each other. Now, I'm going to do some little tricks here to visualize this. Again, similar to what I did before. I'm going to right click and add a column. I'm going to use that custom integer again. We'll set all these values to 1. So all the custom integers for the things in the cut have a value of 1. And then I'm going to close out of here, and then we can go visualize this. So what I'm going to do is I built a little diagram. Let me just build the diagram to show you how quick it is. So because this is a synthetic case and it was made from scratch to have all this data in it, it has latitude, longitude for every bus. So if I go in here and I go auto insert borders, I can put the borders in. I can then auto insert the buses in the case. They're in the substations. If I look at, you would know what's in your case. Hopefully, if I look at the buses themselves, they don't have latitude, longitude coordinates, but if I look at the substations, they do have latitude, longitude coordinates for all of them. So when I go to auto insert buses on my one line, I'm going to insert them by saying, get the latitude, longitude coordinates from the substation records. I'm going to insert on top of the map projection I have. I'm going to insert buses. Well, they aren't on the diagram. And I'm going to go ahead and auto insert lines as soon as it's done too. So if I do that, it's going to lay out all the subs and insert all the buses and then insert all the transmission lines. And this goes pretty quick considering it's 82,000 buses. I'm not going to zoom in on this. I will briefly, just to show you what a mess it is when you get close up, but it's just building in everything. Oops. So there it is. Oh, I didn't auto insert the line. So then if I hit auto insert lines, gens, and shunts, just give this a second. It's useful to do a live demo just to show you, hey, this doesn't take as long as you think if you have all this geography. What takes time is laying it out so it looks pretty when you zoom in. That literally takes months if you want it to look nice. But for what we're doing, we don't really need it to look nice because we're just looking at it from a high level. So there's our thing. So if we zoom in into our case, it's kind of a mess when you get in here. Kind of is an understatement. But the point is we can use this diagram then. Well, it's a cooking type show, so let me grab the one I had already built here. Min cut example. Just open that one because I have some features I've added to it to make it look nice. So what I did with this is I set it up so that it uses an emphasis filter. Again, a feature not a lot of people use, but it's part of one-line display options. And it says, I want to emphasize any of the background lines so I can see the state borders. And I want to emphasize any transformer or transmission line that meets this filter. And the filter says that the custom integer is equal to 1. And emphasize, it really means I de-emphasize everything else. So when it does that, you can see everything's kind of grayed out except these splotchy things here. And then I also set up some dynamic formatting. Actually, it was just on active one line. Or no, you know what? I just selected them. I think I just literally selected them and made them thick so you can see them. Another thing I could do is I could contour. I have this set up to contour based on the area number. I happen to set it up so it looks good to highlight Indiana and the states that are up in the upper right. So I use contouring to highlight my facility is the entire state of Indiana. My external system is the Northeast, and then the minimum cut is these branches here that it found. It just kind of gives you some examples of what that would be useful for. All right, I have that minimum cut. I might then use it in conjunction with another tool in PowerWorld. If I go to Tools, Connections, there's a feature that says Set Selected Field for Network Cut. All right, this is the opposite kind of thing. This assumes that I have a network cut, that I know that I have a list of lines. If I open them, they will split my system into 2 sections. So I have to specify that cut. I'm going to go here and choose branches. The way I'm going to choose them is I'm going to use that filter I just made shortly ago, which was branches that have a custom int equal to 1. And that will give me the 21 transmission lines here and transformers. And if I select all these, there's select all, select all, add them to my cut. So here are the lines and transformers that will split the system. It's those highlighted ones in there. And then I have to choose, I have to tell simulator what is inside the cut. So it's like the cut splits the system in two. Well, part of it we're calling inside and part of it we're calling outside. I'm going to say that the outside here is Auburn because I know that that's in Maine somewhere. So if I do that, then I go to set selected field. I could go back to here. And I'm going to set all the buses so that if they're inside the cut, their selected value will be set to yes. So bus, set selected field to yes, and I can hit OK, select these buses. It says, would you like to initialize all of the other objects, the buses, to no first? In this case, yes, I do want to do that. So I'm going to say yes. All right, at this point, I could go look at it in a table. I'm looking at buses. I look at the custom field selected. It's going to be yes for everything in those first three areas, obviously. And then as you get further away, they'll be mostly no. But let's look at it on the diagram. I could go in here to this emphasis filter again. And I could change it and say, you know what, let's go ahead and change this filter so that I want to emphasize any branch that has a custom integer of 1 or it's selected. Selected, oh yeah, equal to yes. And I just changed that advanced filter. So if I click on here, it's going to have change for this one too, because it's just pointing at it. Yes, it has. If I want those, and then I also want to highlight, let's say, any bus that has selected. Oh, actually, I did that wrong. Selected equals yes, bus selected. As I think about it, I did that wrong. I need to go back here. I didn't select branches. The branch objects, yes, no, selected field did not get populated. I populated the bus one. So this is not what I wanted to do. Instead, what I wanted to do was use another filter and use the filter I just made, which was the bus objects bus selected. And again, it'll do an or, so if either end is set. Then I can hit emphasize and hit OK. Oops, what did I do wrong? The buses are emphasized. Oh, I forgot to put or. That's what it is. I made my filter. I said the custom int is equal to 1 and its bus is selected. I want or. If I do or, then it will work. Yay. So now you can see that the things that were on that side of the network cut. It's just showing you some visualization tools, but the network cut stuff you would use in some other way. All right, I think I'm going to pause for a second. I see if there were any questions so far. I probably should have done that sooner. Scott, have there been any? I got a couple chats here.
Yeah, there's just a comment from Ben. He appreciates the directed graph treatment of that was back when you were discussing the circulating megawatt or megavar flows.
Yes. No, and Ben, you're at a company that could encourage people to fix things. So do that. I mean, I don't want to overplay. These aren't like enormously bad things. They've been around in power flow cases forever. But this is a tool that could make them easy to fix. So why not do it? All right, so here we are. We're back here. Next step is finding radial bus paths. All right, so a radial bus path this is another brand new tool. People have been looking for ways to figure out where do I have parts of the system that are completely radial. Often they're trying to find, if I've got a transformer in series with a bunch of stuff and then a generator at the end, just like no matter what you do, you're going to have an overload on that transformer if the generator output's too high. And just finding those radial paths can be useful. When we're doing this calculation, there are three different options. One of them, there we go. One of them is, should I traverse branches that are open? I think the default is to not do that, but I mean, who knows? Maybe you're just looking for the topology. You don't really trust the present status of anything anyway. So do I want to traverse open branches? Yes or no? The next option is, should I treat, like if I look at this example here, should I say that bus 11 is part of a radial path going up to bus 41? It's clearly a radial path up to 32, but do I treat the parallel branches as part of a radial path? Yes or no? That's another option. And then traverse by. And full topology models, it can be helpful to group together what we call superbuses. If you were to close all the branches in the system, they would be like what we call subnets. So, this maybe you would say that bus 61 is part of a radial path going down to bus 11 because I don't care about the switching topology inside the superbus. So that's what this traverse by superbus would be helpful for. So those are the options. Now, if I go back to simulator, I think I did this on, yes, the data check example. Shoot. One second. All right, so if I go to, where's it at? Find radial bus paths. All right, so in this example, this is a real case. I open it, I can hit calculate radial bus paths, and it will show me, it sorts them, it adds a radial path length. So what I'm seeing here is this particular bus is the terminal bus. Not terminals, not a good word. That means something else in our world. It's the terminating, it's the final bus. So in this case, it's 11. Or not 11, sorry, 61, it's the top bus. Yeah, the radial length. So it starts at 6.4. No, it's I keep saying this wrong. It is the final end. It's the one at the very end. So if I look at 64613, if I just pull up the bus view, it will be obvious. Yeah. So this bus is at the end of a radial path going up here. And this is an example where when I looked at the bus view, I was like, there's not 11 buses in this path. There's fewer than that. But when I came out here to this point, one of the branches here is open. And I said, I did not check the box to traverse open paths. So it's just treating this as though it's not there. And then it continues on up here to the final bus is 64605. Yeah, which is this one. So it's finding those radial paths. The results that you get when you do this calculation is on a bus table. So this is a list of buses here. If I look, there is a neighbors radial path, and there's an end number, an index, and a length. So this is just telling you what's the end number, which index am I. This list is going to have the index 1, meaning it's the first one in all of them. But if I go over here to buses, the index, if I look at 1, those are the ones that are at the very end. Twos are the ones that are the second bus, threes, fours, and so on. And then the radial path length is just telling you in the path that it's in, how long is it? And then there's similar fields on a branch. So if I go back to the image here, basically this guy will be index 1, 2. Tell you what, let me clear this thing. So this is 1, 2. If I'm doing it by superbus, this would be 3, 4, this would be 5, and this would be 6. And those are the indexes of the buses. The indexes of the lines, this is 1, 2, 3, 4, and 5. So 1, 2, 3, 4, 5. Actually, this guy won't be have an index. So that's how it gets labeled, so you can kind of parse the output. All right. All right, next one, under connections, find parallel AC branches. All right, what this is good for is if I do the calculation, it's looking for branches that are parallel with each other. And when I check this box here to identify parallel branches with conflicting tap orientation, this is in there again to help you fix your case. It's not like something's wrong with the case. It's just something that's more confusing than it needs to be. That's what I would say. So in this example, I've got 3 transformers here. If I pull up the bus view, you can see they're right here. What's going on is they're all parallel with each other. If I look at the tap ratios, just glancing at the numbers, I might go, oh my gosh, they're way out of balance. But if I look more carefully, we recently added a little indication on the transformer symbol that says this is the from bus side of the transformer. It's got 2 parallel lines instead of just one jaggy line. And the from and to designations are flipped. So as a result, this one is approximately 1 over this tap. So they're in balance, but it's confusing. It's like, I don't think the modeler who put this together intentionally did this, because it just makes things more confusing. If there's actually a variable tap, yeah, I don't really know the hardware to say this with like 100% certainty, but I doubt they would put the variable tap on opposite sides of parallel transformers. That seems odd. But I guess a hardware person could tell me, no, you might do that, but it seems unlikely. So this is a good tool for finding those. All right, I believe this is the last tool. Yep, the last tool I want to talk about today is what we call breaker isolated groups. And this tool is useful mostly when you have a full topology case. So I'm going to open up a full topology case here that's all anonymized. So all the buses say bus 1, bus 2, bus 3. So it's can't really tell what it is. And I'll go to connections. And there's an option here for breaker isolated groups. So that's where the option is at. This is most useful on a full topology case. What is going to look for is it's going to look at the topology of the system, and it's going to look for a group of breakers that would isolate a portion of the system. So it'll like look at a particular bus, do a graph search outward from that bus looking for breakers. And then the set of breakers that it finds, it'll say, you know what, if those all open, they will isolate all the buses in that pocket together. And then this will give you groupings of those buses so that you know, hey, these transmission lines will all go out together. They're all part of the same switching part of the system. There is also an alternative where if you don't have the topology of the system, you on a bus, there is a field under topology called implicit breakers. By default, these are all set to no. The only thing this implicit breakers is used for is this tool. And what it means is we assume at that particular bus, if I set this to yes, that every device connected to that bus has a switching device of some sort at that end of the device. It's basically treats that bus like it's a single bus, single breaker. It's like everything has a breaker at this bus. Probably not actually true, but it can be useful to say, I'm looking at a 69 kV system and I've got a series of buses, none of which have any switching equipment, or I shouldn't say switch. They don't have any, fault clearing equipment at them. And so I might mark the two buses at the end of that series as implicit breakers and the ones in the middle not. And then this algorithm will also work based on that as well. So all you do to use this tool is, okay, come in here, breaker isolated groups, and you just hit find isolated groups. By default, it's going to base it on the present status of the branches. If you wanted to use this tool and assume all the branches are closed, we don't actually have an option. We just tell you go close all the branches. There is an option though to say use the normal status of the branch if you want. But if I hit calculate on that, it's done. Happens very quickly. If I look at it, it assigns a breaker group number to each bus. And those represent groups of buses that would be isolated by opening switching devices. And each integer, it's just counting upwards. It is one of those groups. So what I could do here, let's say I was interested in 57. I could make an advanced filter here that says the breaker group number is equal to 57. And then I get the buses that are in that group. I could then go over to branches. And if I want the tie lines, I can search in here for 57. And that's not going to work very well. Let's just sort. So here are branches in those group, but I don't really want these ones here because these represent devices inside the grouping. What I really want is, what are the ties that go to that? So what I can do is I can come into my branch table. I can make a filter that says the branch topology group is equal to 57. And that's the branch topology group at the from bus. And then I can do topology breaker group at the to bus equal to 57. And this is about the only time I ever use this XOR. It's like I don't want OR, because if they're both 57, I don't want to see them. I only want it if only one of them is true. So I want XOR. And here's the list of breakers that would isolate that group if I add the topology branch device type here. Oops. You can see they're all breakers and disconnects, which is what I would expect them to be. All right, so that tool can be very useful. You might use this to help make contingencies. PowerWorld actually has a feature in the contingency analysis tool when you're auto inserting contingencies where it says auto insert by bus grouping. That's what that option on this auto insert tool is using the same calculation as I just showed you. So I guess in summary, the connections tools, these are, they're a hodgepodge of things that can make your life easier. So I just encourage you to look at them, kind of revisit them. And then as I went through, I just showed you there's a lot of nice visualizations you can do if you have the geography very, very quickly. I mean, what I showed you, I did in real time here, so it's very easy to add. So see if we have any other questions. Yeah, somebody's asking if I'm going to share the slides. Yes, Scott will put these slides out, and he will also include this video on our website. All right. There any other questions? Any other ideas of things related to this that we might add? I will say most of these have been added because customers have asked for them. I think I could say all of them.
All right. Thanks for sharing with us today, Jamie. And thank you for everybody who joined. And we hope you can join us next week when Tom will talk about integrating our GIC, geomagnetic induced current tool, with the EPRI GICHARM tool, which helps do like the integrated harmonic analysis and analyzing elements that might trip due to harmonics during a GMD, and then processing that back through the power flow. So we'll see you then. Thank you.
All right.